The atoms in your hands right now were born in a cosmic catastrophe. We are often told we are made of stardust, but the most vital elements for life have a far more violent origin. This video will reveal the full story of how colliding neutron stars forged the building blocks of our world and our very bodies. You will understand how gold, iodine, and other essentials journeyed from the most powerful explosions in the universe to become part of you. How can the universe's most destructive events be responsible for its greatest creations? And what does a stellar collision from billions of years ago have to do with the planet you stand on today? What does it mean to you, knowing your own existence is tied to such a distant, violent beginning? To grasp how such violence gives rise to creation, we need to meet the architects, neutron stars. Think of a star many times more massive than our own sun. After it lives out its life, it does not fade quietly. It explodes in a supernova, an event so bright it can outshine an entire galaxy. What remains after that colossal detonation is not emptiness, but a cosmic diamond. This is the neutron star. All that immense stellar mass, often more than our entire sun, is crushed into a sphere no wider than a city. This creates an object of almost unimaginable density. If you could bring a single sugar cube-sized piece of a neutron star to Earth, it would weigh not pounds or tons, but billions of tons. The forces at work here are so extreme that they squeeze atoms themselves out of existence. Electrons are forced into protons, merging to form neutrons. The entire star becomes a solid ball of these subatomic particles, a single, city-sized atomic nucleus. This bizarre state of matter creates gravitational fields that bend light and magnetic fields trillions of times stronger than Earth. It is an environment where the normal rules of physics are stretched to their absolute limit. Yet, within this realm of extreme pressure and density, the seeds of future worlds are held in waiting. The stage is set, but the real magic requires a catastrophic encounter. For a long time, the universe seemed to be keeping a secret about its most valuable treasures. We knew where the common stuff came from, the carbon in our bones and the oxygen we breathe, forged in the fiery hearts of stars. But the origins of the heavy, precious elements, the gold in a wedding ring or the platinum in a catalytic converter, remained a cosmic locked box. These elements are heavier than iron, and creating them requires a special kind of alchemy that ordinary stars and even supernova could not fully explain. Supernova are spectacular, but when scientists ran the numbers, the amounts of gold and other heavy elements they could produce just did not match the abundance we see in the universe. There was a glaring hole in the story of how everything was built, a missing chapter in the recipe for our cosmos. This mystery pushed scientists to consider even more extreme possibilities, and their search led them to a specific and dramatic setup: two neutron stars locked in a fatal dance, circling each other in a binary system. Many of the universe's most massive stars do not live alone. They are born in pairs, two stellar siblings bound together by gravity from their very first moments. When both of these stars are true giants, each one ends its life in that spectacular supernova we described, leaving behind not one, but two of those impossibly dense neutron stars. Now the real drama begins. These two cosmic diamonds, each containing more mass than our sun, are now trapped in an intimate, swirling orbit around each other. This is the binary neutron star system, a pair of the most perfect compact spheres in existence, engaged in a gravitational waltz that can last for eons. They are not static, though. Einstein's theory of general relativity predicted that such massive objects moving through space-time would create ripples, gravitational waves that carry energy away from the system. This slow, steady loss of energy has a profound effect. It causes the two stars to spiral inward, closer and closer, their dance growing faster and more frantic with every passing millennium. Think of it as the universe's slowest countdown, a celestial prelude lasting hundreds of millions of years, all building towards a single, inevitable, and catastrophic moment of collision. All that time, all that slow, creeping motion, is storing up an unimaginable amount of potential energy, waiting for the instant it will be unleashed in a flash that forges the very elements of life itself. This silent song of spacetime is our first real-time clue to the unfolding drama. For over a century, Einstein's theory of general relativity told us that massive, accelerating objects should create ripples in the fabric of the cosmos, distortions that travel outward at the speed of light. Yet detecting these gravitational waves seemed almost impossible, a whisper lost in a cosmic hurricane that changed with observatories like LIGO and Virgo, instruments so sensitive they can measure a change in distance thousands of times smaller than a single proton. What do they listen for as the two neutron stars in their final death spiral whip around each other thousands of times per second? They pump immense energy into spacetime itself. The waves they emit grow rapidly in both amplitude and frequency, creating a signature signal that scientists call a chirp. It is not a sound you could hear in air, but if you translated the ripples into an audio tone, you would hear a rapid, rising whistle, the literal sound of impending collision. This ghostly signal is the universe's way of sending out a silent alert, a telegram written not in light but in the warping of space and time. It allows us to pinpoint the location of these incredible events and opens an entirely new sense with which to observe the cosmos. We are no longer just stargazers, we have become universe listeners, hearing the echoes of creation itself. This final, frantic dance ends in a flash of cosmic violence. The two neutron stars, each packing the mass of our entire sun into a city-sized sphere, finally cross a point of no return. In their last millisecond, they accelerate to nearly half the speed of light before they collide. The impact is not a gentle merging. It is a shattering event, a detonation so powerful it outshines for a brief instant the combined light of every star in every galaxy we can see. The sheer force of this collision does more than just push material around. It shreds the outer layers of both stars, flinging a cloud of their innermost substance out into the void. This ejected material is not just stardust, it is a soup of free neutrons, the fundamental building blocks that were locked inside those ultra-dense objects. This is the crucial first step, the gathering of raw ingredients. But what happens to the hearts of these colliding stars? Their cores do not get ejected. They plunge into one another, merging into a single, unstable object. For a fleeting moment, this new creation can form a hyper-massive neutron star, a trembling, quaking sphere that is simply too heavy to hold itself together. In most cases, it lasts for only milliseconds before its own immense gravity causes it to collapse in on itself, forming a newborn black hole. This instant of collapse sends another tremendous shockwave through the surrounding cloud of ejected material. It is this 1-2 punch, the initial collision and the subsequent collapse, that supercharges the environment and kicks off the most important chemical process in the universe. The stage has been violently set, and now the real alchemy can begin. This brilliant flash of light is the kilonova, the universe's ultimate forge. It is a cosmic firework of staggering proportions, yet one that fades in just a few days. The light we see is not from the heat of the collision itself, but from the radioactive glow of newborn atoms. As the cloud of ejected neutron star material expands, it is saturated with free neutrons. These neutrons are the key ingredient in a frantic cosmic process known as the rapid neutron-capture process, or the R process for short. Think of it as the most intense assembly line imaginable. Atomic nuclei are bombarded by a blizzard of neutrons, one after another, so quickly that the nucleus does not have time to stabilize between captures. This rapid addition forces the nucleus to grow heavier and heavier, climbing up the periodic table in a matter of seconds. It is through this explosive chain reaction that the heaviest and most valuable elements are born. Gold, platinum, the iodine essential for your metabolism, and the rare earth elements in your smartphone, all are forged in this single, spectacular event. The light from the kilonova is not just a flash, it is a broadcast. When astronomers analyze its spectrum, they see the clear, telltale fingerprints of these heavy elements. The red and infrared glow of a kilonova, distinct from the blue light of a supernova, is literally the color of cooling gold and other cosmic metals. This observational proof confirmed a long-held theory, revealing that these collisions are the universe's primary factories for the elements that make up our technology, our economies, and the very chemistry of life. This frantic assembly line, the R process, is the true engine of creation within the kilonova's fire. It all comes down to an overwhelming flood of neutrons. Picture an atomic nucleus, a tiny cluster of protons and neutrons caught in this storm. It is hit by a blizzard of free neutrons, one after another, so quickly that it cannot even process the addition. The nucleus absorbs them faster than it can naturally shed the extra energy. It is like trying to catch an avalanche of tennis balls, your arms piling high before you can even throw a single one back. This rapid, relentless capture forces the nucleus to swell, becoming a heavier and heavier isotope in a matter of seconds. It climbs the periodic table at a breathtaking pace, from a simple element like iron all the way up to the most massive atoms in existence. But these newly forged, super-sized nuclei are deeply unstable, bloated with far too many neutrons. They are like overfilled balloons, desperate to find a stable form. Once the furious neutron bombardment subsides, a second act begins. Each of these unstable nuclei undergoes a quiet, internal transformation known as beta decay. One by one, the excess neutrons convert into protons. This subtle shift is the final, crucial step that solidifies the creation. As the number of protons increases, the atom settles into its permanent identity, becoming a stable, heavy element. In just a few seconds, this 1-2 punch of rapid capture and subsequent decay forges about half of all elements heavier than iron. The silver in a photographic film, the uranium that powers reactors, the xenon used in specialized lighting, all were born from this brief, violent sequence. It is the universe's most efficient factory, turning a cloud of subatomic particles into the very building blocks of our modern world. But the story does not end with that brilliant flash. The kilonova acts as a cosmic cannon, firing the newly forged elements out into the void. This cosmic shrapnel, a cloud of atomic nuclei including gold, silver, and iodine, is ejected at a significant fraction of the speed of light. It carries with it a mixture of lighter elements, creating a vast, expanding bubble of enriched material. This is the universe's ultimate recycling program in action. The precious metals and essential elements are violently scattered, their journey from a single, catastrophic point now beginning in earnest. They travel for thousands, then millions of years, their paths intertwining with the cool, dark clouds of gas and dust that drift between the stars. As this expanding cloud travels, it gradually cools. the frantic, energetic atoms begin to slow down and stick together, condensing around microscopic motes of carbon and other minerals. They form tiny, solid dust grains, each one a speck of stardust carrying within it the legacy of that ancient collision. These minuscule grains, no larger than a particle of smoke, are the seeds of future worlds. They become the raw material that will one day collapse under gravity to form a new star, and surrounding it, a family of planets. This ejection phase is the critical distribution step, a cosmic scattering of the elements that ensures the products of a rare and violent event in one corner of the galaxy can eventually find their way to another. Without this dispersal, the building blocks of life and civilization would remain locked in isolated pockets of space, unable to fulfill their ultimate purpose. This galactic recycling program is the final, essential step in our story. All those heavy elements forged in the kilonova's fury are now cast adrift, but they are not lost. They drift for eons through the vast, cold expanses between stars, eventually mingling with the raw, primordial gas of giant molecular clouds. These clouds are the universe's nurseries, immense and dark, composed mostly of hydrogen and helium left over from the Big Bang. The arrival of the enriched material from stellar collisions is what transforms these simple clouds into something far more potent. It seeds them with the heavy elements necessary for complex chemistry, the very ingredients that will one day become rock, metal, and ultimately life itself. Within these cold, dark clouds, gravity begins its slow, patient work. A slight disturbance, perhaps the shock wave from a nearby supernova, causes a dense pocket to begin collapsing under its own weight. As this pocket spins and flattens, it forms a new star at its center, surrounded by a vast, swirling disk of gas and dust. This is a protoplanetary disk, the birthplace of planets. And scattered throughout that disk, like microscopic treasures, are those same dust grains that condensed in the aftermath of the kilonova. Each speck contains atoms of gold, iodine, and other heavy elements. Within the disk, these grains begin to stick together, colliding and coalescing into ever larger objects. They form pebbles, then rocks, then planetesimals, and finally, full-fledged planets. The iron in Earth's core, the silicon in its rocky crust, and the gold veins running through it, all were once part of that cosmic dust. Our entire solar system, from the Sun to the farthest comets in the Oort cloud, condensed from one of these enriched clouds over 4.6 billion years ago. So the gold in a wedding ring is not just a metal, it is a time capsule. It is a physical fragment of a cataclysm that occurred long before our Sun even ignited. The iodine that regulates your metabolism, allowing you to think and feel, was created in a flash of unimaginable violence and delivered across the galaxy to become part of you. Your connection to the cosmos is not just poetic, it is profoundly physical, written into the very atoms that construct your body and the world you walk upon. For decades, the violent birth of heavy elements was a beautiful theory waiting for proof. That proof arrived on a quiet August day. On August 17, 2017, gravitational wave observatories recorded a distinctive chirp, the unmistakable sound of two neutron stars spiraling into one another. For the first time, this cosmic ripple in spacetime was not alone. Mere seconds after the gravitational signal, NASA's Fermi Space Telescope detected a short, powerful flash of gamma rays from the exact same patch of sky. This one-two punch of gravitational waves and light set off a global scramble, an unprecedented hunt across the cosmos. Astronomers worldwide pivoted their telescopes, both on the ground and in space, toward the source. They pinpointed the event to an ancient galaxy, 130 million light-years away, in the faint constellation of Hydra. What they witnessed over the following days and weeks was the rise and fall of a kilonova, its light shifting from blue to a profound, glowing red. This event, catalogued as GW170817, was the smoking gun. It was the first time we had ever observed the same cosmic event through both gravitational waves and light, a new field called multi-messenger astronomy. The data was a perfect match, the red glow of the kilonova carrying the specific chemical fingerprints of heavy elements like gold, platinum, and tellurium being forged in real time. This single observation transformed a compelling hypothesis into established fact, confirming that the gold in your jewelry and the iodine in your body were indeed born from the most powerful collisions in the universe. With the confirmation of that single event, our entire understanding of the periodic table was rewritten. It is no longer just a chart of chemical elements, but a historical document chronicling the universe's own biography. Each element holds a memory of its violent cosmic birth. The very first pages of this story are written by the Big Bang itself, which forged the two simplest elements, hydrogen and helium, in the searing heat of the universe's first moments. For billions of years, these were the only building blocks that existed. Then, the first stars ignited. Within their nuclear furnaces, they began the slow process of fusion, cooking lighter elements into heavier ones, creating the carbon for life and the oxygen for water, all the way up to iron. But here, the story hit a wall. Creating any element heavier than iron does not release energy, it consumes it. A star's factory grinds to a halt. For decades, the origin of the elements beyond iron, the gold and the silver, the iodine and the uranium, was the great missing chapter. Now we know that chapter is written in the collisions of neutron stars. The detection of strontium and barium in the light of the kilonova was the final piece of evidence, a direct chemical fingerprint linking a specific, observed event to the creation of these specific, heavy materials. This completes our map of cosmic nucleosynthesis, the grand story of where every atom comes from. So when you look at the periodic table, you are not just seeing a grid of symbols and numbers. You are reading a timeline. You see the primordial hydrogen from the beginning of everything. You see the carbon forged in a long dead star. And you see the gold created in a spectacular collision that seeded the galaxy with the possibility of planets and ultimately of us. These microscopic dust grains, forged in stellar fire and scattered by cosmic violence, are the true seeds of planets. Picture the swirling chaos of a young solar system, a vast, flat disk of gas and dust spinning around a newborn star. Within this maelstrom, our enriched dust grains begin a slow, stately dance. They drift, they bump, they gently stick together through nothing more than static forces like cosmic Velcro. This is how pebbles are born from smoke. Over thousands of years, these pebbles gather into larger rocks, and the rocks, in turn, begin to pull each other together with their own tiny gravitational fields. They are no longer just loose collections of dust, but are becoming the foundational building blocks of worlds called planetesimals. These are the planetary embryos, some no larger than a city, others as vast as a small moon, now orbiting the young sun. Yet, without a crucial ingredient from those stellar collisions, these fledgling worlds would remain frozen and geologically dead. That ingredient is a specific type of aluminum, known as aluminum-26. This element is radioactive, and as it decays, it releases a steady, internal heat. Think of it as a built-in furnace buried deep within the rocky body of a planetesimal. This radioactive warmth is the spark that transforms a cold, inert lump of rock into a dynamic, evolving world. The heat begins to melt the planetesimal from the inside out. As it melts, a profound transformation occurs, one that defines the very structure of planets like our own. The heaviest materials, the iron and nickel forged in that long-ago kilonova, are now liquid and dense. Drawn by gravity, they sink relentlessly downward, pooling at the very center to form a metallic core. Meanwhile, the lighter, rocky silicates rise to the surface, cooling to form a primitive crust. This process, called differentiation, is what creates a planet with distinct layers. It is the birth of a core that can generate a protective magnetic field and a crust that can host continents and oceans. Without the heavy, radioactive elements delivered by stellar cataclysms, planetesimals would lack this internal engine. They might never melt, never differentiate, remaining simple and homogeneous. The result would be a solar system filled with unremarkable, icy asteroids, with no rocky planets, no metal cores, and no chance for the complex geology that makes a world like Earth possible. The violent death of ancient stars did not just provide the raw materials for planets, it provided the very warmth that brought them to life. Deep within our planet, a slow and steady warmth has burned for over 4.5 billion years. This is not the lingering heat from Earth's violent formation, but a fire sustained by the very atoms created in those ancient stellar collisions. The uranium and thorium forged in the kilonova's heart are not merely inert ingredients, they are tiny, persistent power plants. Each atom is unstable, and over an unimaginably long timescale, it gently falls apart, releasing a small pulse of energy with every decay. This process, known as radiogenic heating, is the hidden engine of our living world. It is a distributed warmth, a gentle and constant geothermal fire that keeps the interior of our planet dynamically alive. Without this internal furnace, Earth would have cooled into a geologically dead sphere long ago, a frozen rock with a solid, motionless interior. Instead, this radiogenic heat sets the entire planet in slow, churning motion. It drives the massive convection currents in the mantle, the thick, rocky layer beneath the crust. Think of a pot of soup simmering on a stove, the heat from below causing the liquid to rise, cool, and fall in a continuous, cyclical flow. On a planetary scale, this is the force that breaks the crust into plates and sends them drifting across the globe. This relentless geological recycling, known as plate tectonics, is far more than just the cause of earthquakes and volcanoes. It is a global thermostat. As tectonic plates collide and slide, they pull carbonate rocks deep into the mantle, locking away carbon, and then later release it through volcanic eruptions. This endless cycle has, for billions of years, regulated the amount of carbon dioxide in our atmosphere, stabilizing the climate within a range that could nurture life. But the influence of these radioactive elements reaches even deeper, to the very heart of the planet. The heat they generate helps maintain the outer core as a swirling ocean of molten iron and nickel. This liquid metal, set in motion by Earth's rotation and the heat rising from within, acts like a colossal dynamo. It generates our planet's magnetic field, an invisible shield that extends far out into space. This magnetic bubble deflects the constant, damaging stream of charged particles from the sun, the solar wind. Without this protection, our atmosphere would have been slowly stripped away, leaving the surface exposed to harsh radiation and making the world a barren desert. So the gold in a ring is a relic of that cosmic collision, but the uranium deep underground is its active legacy. It is the enduring gift from a stellar cataclysm, a steady heartbeat of heat that powers the geology and generates the shield that keeps our world safe and alive. This biological connection runs deeper than gold or uranium. The same violent stellar forges that created precious metals also produced the very elements that make complex life possible. Consider iodine, a substance you might only know from antiseptic or table salt. Inside your body, iodine is anything but simple. It is a fundamental building block of the thyroid hormones that act as the master regulators of your metabolism. These hormones control how your body uses energy, setting the pace for everything from your heart rate to your brain function. Without a steady supply of iodine, this entire system falters, leading to serious health challenges. Your ability to think, to grow, and to stay warm is directly governed by an element that was absent from the early universe until a neutron star collision forged it. Similarly, selenium, though needed in only minute amounts, plays an outsized role in your survival. It is a crucial component of powerful antioxidant enzymes. Think of these enzymes as a cellular repair crew, constantly mopping up the damaging byproducts of your body's own energy production. This internal cleanup protects your cells from premature breakdown and supports a healthy immune response. Then there is molybdenum, a name you might never have heard. This metal is a key part of enzymes that allow organisms, from bacteria to humans, to process essential elements like nitrogen and sulfur. It helps convert dietary nutrients into forms your body can actually use, a quiet but vital part of the chemistry that keeps you alive. These three elements, iodine, selenium, and molybdenum, are all trace nutrients required only in tiny quantities. Yet their absence would make complex animal life, as we know it, impossible. Their presence on our planet is not an accident. It is a direct inheritance from the enriched cloud that formed our solar system, a cloud that was seeded with these biological essentials by stellar explosions that occurred long before the sun was born. Your body's most fundamental regulatory processes are thus guided by atoms with the most extraordinary cosmic history. The gold in your hand is a time capsule from a distant, violent past. Every single atom of that gleaming metal was born in the furnace of a neutron star collision that likely occurred billions of years before our own sun even ignited. That cataclysmic merger acted like a cosmic cannon, firing a cloud of newly forged elements, including gold, out into the void at incredible speeds. For eons, these atoms drifted through the vast, cold emptiness between stars, a silent and invisible treasure. Their journey only ended when they were swept up by the gentle pull of a giant molecular cloud, the very nebula that would one day collapse to form our entire solar system. As our planet coalesced from the dust and rock within that swirling disk, it gathered these precious particles, incorporating them deep into its metallic core and rocky mantle. The gold we find in veins near the surface today was delivered by asteroids that bombarded the young Earth, acting as final delivery vehicles for this cosmic cargo. So when you hold a piece of gold, you are not just holding a precious metal. You are holding a physical fragment of one of the universe's most powerful explosions. It is a tangible, direct connection to an event of unimaginable violence and creative power, a relic that has traveled across space and time to end up in the palm of your hand. This cosmic assembly line, however, runs on a very strict and infrequent schedule. While supernovae flash across the cosmos perhaps a few times per century in a galaxy like ours, the merger of two neutron stars is an event of profound rarity. Astronomers estimate such a collision happens only a handful of times every million years in a typical galaxy. Think about that timescale for a moment. Our own Milky Way has witnessed the rise and fall of countless stars over its 13 billion-year life. Yet the number of these specific element-forging collisions remains remarkably low. This cosmic scarcity is written directly into the composition of our planet. Look at the ground beneath your feet. It is rich with silicon and oxygen, iron and aluminum. These are the common materials of our world because they are the common products of stellar furnaces, forged in the vast populations of ordinary stars and in more frequent supernova explosions. But then consider gold, Its dazzling gleam and cultural value are not merely human inventions. They are a direct echo of its extraordinary origin. The same is true for platinum, an element even more scarce in Earth's crust. Their economic preciousness is, in a very real sense, a measure of their genuine cosmic preciousness. The market value we assign them is a faint reflection of the immense energy, specific conditions, and sheer improbability required to create them. They are not just rare in a vault, they are rare in the universe. Every gold ring is therefore a concentrated piece of cosmic history, representing not just one star's death, but the perfect, synchronized demise of two, and the incredibly unlikely chain of events that brought those atoms to our solar system. The very reason these metals are dug from deep within the Earth is because their scarcity began not here, but in the profound emptiness between the stars, in the long, patient wait for a collision that would, for a brilliant instant, fill the void with creation. To witness the heart of such a cataclysm, we must turn to digital worlds. Supercomputers now allow us to recreate these collisions, not in steel and vacuum, but in lines of code. These are not simple animations. They are full-scale virtual universes governed by the unbreakable laws of physics. Each simulation must account for the brutal distortions of general relativity, the complex dance of nuclear forces, and the behavior of swirling, magnetized fluids. It is a mathematical symphony of chaos, calculating the fate of two city-sized objects from their final, frantic orbits down to the moment their cores merge and collapse. The goal is to see the unseen, to trace the journey of a single neutron as it is flung from the wreckage and begins its transformation into a stable, heavy atom. These digital forges reveal precisely how much golden, life-giving material a single collision can produce, and what kind of light show that creation should emit. Without these virtual experiments, the brief flash of a real kilonova would be just a mysterious blip of light. The simulations provide the decoder ring, translating that fleeting glow into a detailed inventory of newly forged elements. They guide astronomers, telling them exactly what chemical fingerprints to search for in the light of distant galaxies, turning a one-time observation into a repeatable experiment that deepens our understanding with every new run of the code. This golden age of discovery hinges on a powerful new synergy between light and gravity. While our current observatories have given us a first, breathtaking glimpse, the next generation of telescopes will transform a rare spectacle into a regular observation. The Vera C. Rubin Observatory, with a camera the size of a small car, will scan the entire visible sky every few nights. It will not wait for an alert, but instead constantly watch, catching the faint, quick glimmer of kilonovae as they ignite in distant galaxies. It could find dozens of these cosmic forges every single year. Simultaneously, the Nancy Grace Roman Space Telescope will peer deep into the infrared, seeing the cool, red glow of heavy elements with a clarity we have never before possessed. But the revolution does not stop with light. On the ground, a new generation of gravitational wave detectors, like the planned Einstein telescope, will be built deep underground to escape terrestrial noise. Its sensitivity will be so profound it could hear the final spirals of neutron stars from the very edge of the observable universe. And in the silent void of space, the LISA mission will launch a trio of satellites to detect low-frequency gravitational waves, opening an entirely new window into the cosmos. This is the power of multi-messenger astronomy evolving into a true census of cosmic creation. We will no longer be studying single, extraordinary events, but populations. By correlating the light from hundreds of kilonovae with the gravitational waves they produce, we can finally answer fundamental questions. How much gold, platinum, and iodine does a typical collision create? How often do these events truly happen across the history of the universe? The data will let us measure the total production of these vital elements across cosmic time, piecing together the complete history of how our galaxy became enriched with the stuff of planets and life. In this flood of new data, we may even find something entirely unexpected, a signal that does not match any of our models, revealing a new type of cataclysm or a bizarre state of matter we have not yet dreamed of. The universe's elemental forges are about to have their doors thrown wide open. Each star in our galaxy holds a chemical memory of its own birth. The faint light from a distant sun, when split into a rainbow-like spectrum, reveals a barcode of dark lines, each one the fingerprint of a specific element. This is how we perform cosmic archaeology, reading the biography of the Milky Way not in ancient texts but in starlight itself. The oldest stars we can observe, known as population 2 stars, are the galactic elders. They formed billions of years ago from the pristine hydrogen and helium left by the Big Bang. Their atmospheres are remarkably pure, containing only trace amounts of elements heavier than helium. This tells a clear story. They were born before the galaxy had been widely seeded with the products of stellar explosions. They are living relics from a time before planets like Earth could even exist, because the very ingredients for rock and metal had not yet been forged in sufficient quantities. Younger stars, like our own Sun, tell a very different tale. Our Sun's composition is about 2% heavy elements. This richer chemical palette reveals it is a star of the modern era, born from a cloud that had been enriched by generations of supernova and, crucially, by those rare neutron star mergers. The specific mix of elements in a star is like a cosmic recipe, and astronomers are the chefs who can discern which ingredients came from which event. For instance, the unique pattern of certain rare Earth elements in a star's spectrum can point directly to a heritage dominated by the rapid neutron-capture process, the R process, that only occurs in kilonovae. A star rich in europium or gold, but relatively poor in elements made primarily in common supernova, likely formed from a cloud that was recently fertilized by the debris of a neutron star collision. By mapping the chemical compositions of millions of stars across the galaxy, we can begin to reconstruct a timeline of these cosmic cataclysms. We can see which regions were enriched first and identify the galactic neighborhoods that have been most productive in creating the elements for life. It is a grand galactic genealogy, tracing our own solar system's ancestry back to a specific series of stellar explosions and collisions that made our world, and us, possible. Yet the universe rarely relies on a single forge. While neutron star collisions are master jewelers for the heaviest elements, they are not the only workshops in the cosmic factory. Core collapse supernova, the spectacular deaths of stars more than 8 times the mass of our Sun, also contribute to this grand production. In their final, violent moments, these explosions create a fleeting storm of neutrons, allowing for a version of the rapid capture process. However, the conditions are often not as extreme or as sustained as in a kilonova. The yield of gold or platinum from a typical supernova is thought to be far lower, a sprinkle of precious dust compared to the torrent produced by a stellar merger. Then there are the more exotic candidates, the cosmic outliers that might hold unexpected keys. Magnetars, for instance, are neutron stars born spinning furiously and endowed with magnetic fields so powerful they could strip information from a credit card from 500,000 miles away. Some theories suggest their incredible energy could power unique nucleosynthesis events. Another frontier of research involves collapsars, which are not just supernova, but the collapse of the most massive stars directly into a black hole, creating a swirling, chaotic vortex of material that might also be a potent element factory. The central question for astrophysicists today is no longer if these events create heavy elements, but how much each one contributes. Is 50% of the universe's gold from mergers and 40% from collapsars? Does the rare magnetar account for a specific, strange element we find in meteorites? Piecing together this cosmic supply chain is like being a detective at the scene of a billion-year-old mystery, where the clues are the elemental fingerprints within the oldest stars. Each new observation helps us understand the precise recipe the universe used to build a world rich enough and complex enough for us to walk upon it. These unimaginably strong magnetic fields transform the collision into an entirely different kind of beast. We have to think beyond just the gravity and the nuclear physics, because when two of these magnetized corpses spiral together, their invisible fields become a dominant player. The stars do not just merge, their magnetic architectures violently intertwine. The lines of force are stretched, twisted, and braided together in a frantic dance. This process can amplify the fields to almost incomprehensible strength, reaching levels a trillion times more powerful than the magnetic field that surrounds our own planet. This creates a colossal reservoir of energy, a kind of cosmic battery that needs to discharge. And it does so in the most dramatic way possible, by focusing and launching narrow, ultra-fast jets of material directly from the poles of the merged object. These jets, moving at over 99% of the speed of light, are now believed to be the central engine behind short gamma-ray bursts, some of the most energetic flashes of light in the entire universe. So that initial gamma-ray signal we detect is not just a side effect of the crash. It is the direct scream of these magnetic jets punching their way out of the cosmic wreckage. But the influence of magnetism does not stop there. It reaches into the very heart of the element forging process itself. The chaotic swirl of debris that forms a hot, dense disk around the newborn black hole is seething with this magnetic energy. The fields can act like a giant whisk, stirring this chaotic soup and changing how material flows. Some elements might be channeled more efficiently into the jets, while others are flung out in wider, slower winds. This means the specific magnetic fingerprint of a collision could directly determine the final chemical mix, altering the ratio of gold to platinum or iodine to tellurium that gets scattered into the galaxy. It adds a profound layer of complexity to our story, suggesting that the ultimate recipe for a planet like Earth may depend not just on a collision happening, but on the specific, invisible magnetic personalities of the two neutron stars that were involved. The merger's final act creates a new kind of monster. In most cases, the combined core is so impossibly heavy that it cannot hold itself up, and it immediately collapses, vanishing from our observable universe to form a newborn black hole. Yet the story of creation does not end at that point of no return. The black hole is left hungry, surrounded by a swirling, incandescent whirlpool of what used to be the outer layers of the two stars. This is the accretion disk, a chaotic maelstrom of superheated matter spinning at near light speed. The physics here is beyond extreme. The particles in this disk are so densely packed that they constantly collide, creating immense friction that heats the entire structure to temperatures of billions of degrees. It is a cauldron of pure energy, kept from falling into the abyss only by its own furious orbital velocity. From the inner edge of this disk, a thin drizzle of material constantly crosses the event horizon, feeding the black hole and making it grow. But the real action for element creation happens further out. Powerful magnetic fields, twisted by the disk's insane rotation, act like cosmic slingshots, flinging vast outflows of material away from the poles and in wider winds from the disk's surface. This material, blasted outward from the brink of the abyss, provides a second, distinct site for the forging of elements. The conditions in these outflows are different from the initial collision cloud. They are slightly less dense, and the neutron capture can happen at a different pace. This subtle variation means the outflows from the accretion disk might produce a unique mix of isotopes, a different chemical signature compared to the material ejected during the impact itself. The final chemical bounty of the entire event, the precise blend of gold, platinum, and other rarities that gets scattered into the galaxy, depends critically on the lifetime and stability of this brilliant, doomed disk. Its brief, furious existence fine-tunes the universe's elemental recipe, ensuring that each stellar collision contributes its own distinct flavor to the cosmic mix. This galactic dispersal is a slow and turbulent voyage. The elements are blasted outward with such force that many achieve escape velocity, breaking free from their home galaxy entirely to drift in the vast, empty space between galaxies. Those that remain within the galactic confines do not settle quietly. They are caught in a perpetual cosmic storm, pushed and pulled by the shockwaves from other supernovae, the constant stream of stellar winds from massive stars, and the slow, grand rotation of the Milky Way itself. It is a churning process that takes hundreds of millions of years, a gradual stirring that mixes the rare fruits of a single cataclysm into the galaxy's general reservoir of gas. This ensures that no corner of the galaxy is permanently isolated from these essential ingredients. The gold forged in a collision on one side of the Milky Way can, over eons, find its way to a quiet, distant spiral arm where new stars are beginning to form. This galactic mixing connects every stellar nursery and every dying star in a single, vast, and interconnected ecosystem. It means the heavy elements essential for building a rocky, life-bearing world are not just local treasures, but a shared inheritance for the entire galaxy, a cosmic lottery where every new solar system gets a chance at the ingredients for complexity. This journey from cosmic violence to planetary life raises a question that echoes through the halls of science and philosophy. We find ourselves in a universe that seems perfectly arranged to produce us. The very processes that forge the elements of life depend on a delicate balance of physical laws. This idea is known as the anthropic principle. It suggests that the universe we observe must be compatible with the existence of conscious life because we are here to observe it. If any of the fundamental constants were even slightly different, the chain of creation would snap. If the force of gravity were a fraction stronger, stars would burn too hot and fast, collapsing before they could produce heavy elements. If the nuclear forces were weaker, the R process in colliding neutron stars might never happen at all, leaving the cosmos devoid of gold and iodine. The strong nuclear force that binds atomic nuclei is tuned with incredible precision. If it were just a few % weaker, protons and neutrons would not stick together, and complex atoms could never form. If it were slightly stronger, the universe might be filled with bizarre, unstable elements, with no stable carbon or oxygen for life. We are the beneficiaries of a cosmic lottery, living in a universe where the dials appear set just right for chemistry, for planets, and for observers. Whether this fine-tuning is a staggering coincidence, the result of a multiverse where countless other universes with different laws exist, or a deeper feature of reality we do not yet understand, remains one of the most profound and humbling mysteries. It bridges the vast, impersonal forces of cosmology with the intimate reality of our own biology, connecting the collision of dead stars directly to the question of our own existence. But if these cosmic forges are so vital to our existence, where is the evidence in our own celestial backyard? The hunt is on within our own Milky Way for the ancient ghosts of these collisions, structures known as kilonova remnants. Unlike the brief, brilliant flash of the event itself, a remnant is the lasting echo, an expanding cloud of gas that has been cooling and drifting for thousands or even millions of years. This cloud would be profoundly enriched with the specific signature of the R process, a bubble of space where the concentration of gold, platinum, and other rare earth elements is far higher than the surrounding galactic average. Finding one of these structures would be like discovering the archaeological site of a legendary battle, giving us a nearby laboratory to dissect the aftermath of a merger in painstaking detail. We could analyze its exact chemical composition, measure its expansion rate, and even use radioactive isotopes within it as clocks to date the original cataclysm. This would allow us to pin a precise timestamp on a moment of cosmic enrichment in our galaxy's history. We could then look at the stars that formed in that region around that time and see if they carry that unique chemical fingerprint, directly linking a single, local event to the birth of new solar systems. So how do you find the ghost of a million-year-old explosion? Astronomers search for unusual, bubble-like structures in the interstellar medium that glow with the specific X-ray or radio signatures of heavy, unstable elements. They look for regions where the gas is too hot and too rich in rare materials to be explained by a common supernova. It is a needle in a haystack search, but the payoff would be immense, transforming our understanding of our own local cosmic history from a vague story into a chronicle with specific dates and addresses. This revelation fundamentally reshapes what it means for a world to be habitable. For decades, we defined a star's habitable zone simply as the orbital region where temperatures could allow for liquid water on a planet's surface. But water alone is not enough. A planet must also possess the complete chemical toolkit for biology, and we now know that toolkit is assembled in the most violent events in the cosmos. A star could have a dozen worlds swimming in warm oceans, but if its planetary system formed from gas that was not properly enriched, those worlds would be barren. They would lack the iodine for complex metabolism, the selenium for cellular repair, and the molybdenum for processing fundamental nutrients. Life as we know it could not get started. This means true habitability has a prerequisite, a cosmic inheritance. A planetary system must be born from raw materials that have been seeded by generations of stellar lives and deaths. The very first stars in the universe, known as population 3 stars, were composed only of hydrogen and helium. They lived fast, died young, and seeded space with the first heavy elements, but not the full suite we require. Their planets, if they had any, would have been gaseous or utterly barren, worlds without the geological complexity or chemical diversity for biology. It took subsequent generations of stars and the rare, crucial mergers of neutron stars to cook and distribute the full periodic table. Our own Sun is a third-generation star, its composition rich with the legacy of countless stellar ancestors. This cosmic timeline implies that life is almost certainly a latecomer in the universe's story. It could not arise immediately after the Big Bang, but had to wait for the galaxy to become chemically mature, for its gas clouds to be sufficiently fertilized with the building blocks of worlds. The habitable zone, therefore, is not just a band of space around a star. It is a window in time, emerging only after a galaxy has lived long enough to forge and scatter the elements of life. It connects the destiny of a potential alien world directly to the explosive history of its entire galactic neighborhood. The universe's creative forges are often misunderstood as agents of pure destruction. It is natural to wonder what would happen if such a cataclysm occurred close to our own world. While the gamma ray burst from a neutron-star merger is indeed one of the most powerful beams of energy in the cosmos, its danger is highly focused. These jets are like the beam of a cosmic lighthouse, incredibly deadly if you are standing directly in their path, but harmless if you are off to the side. Given the vast, random orientations of stellar systems in our galaxy, the chance of Earth being in that narrow line of fire is astronomically small. Furthermore, the nearest known pairs of neutron stars are hundreds of light years away, far beyond the distance where their radiation or gravitational waves could affect our planet. The true nature of these events is also frequently misrepresented. We call them collisions, but they are not explosions like a bomb. There is no fiery shockwave expanding to destroy nearby worlds. Instead, it is a transformative release of energy, a brief, intense flash that acts as a crucible. In that fleeting moment, the very fabric of matter is reworked, forging new atomic nuclei from the remnants of the old. Understanding this shifts our perspective from fear to awe. These are not random acts of cosmic violence, but precise, physical processes that build rather than obliterate. They are the reason our world is geologically active and chemically rich, a testament to a universe that uses its most extreme conditions to create the foundations for life. This grand narrative reveals a universe woven together by a single, unbroken thread of physical law. The journey of a gold atom, from its violent birth to its quiet resting place in your hand, is a story that connects every branch of science. It starts in the bizarre realm of quantum mechanics, where the probabilistic behavior of a single neutron dictates whether it will be captured by an atomic nucleus. This microscopic dance is set on a stage warped by the immense gravity described by Einstein's general relativity, which crushes the neutron stars together. The moment of collision is ruled by nuclear physics, the fundamental forces that bind protons and neutrons, allowing them to assemble into newer, heavier elements through that frantic process. Yet the story does not end there. These newly forged atoms become the raw ingredients for chemistry, enabling the complex bonds and reactions that form rocks, oceans, and atmospheres. Finally, biology takes these same elements and weaves them into the very fabric of life itself. The iodine regulating your thyroid, the iron carrying oxygen in your blood. These are the end products of a chain of events that began with the rules governing the smallest particles in existence. This is not a series of separate events, but a single, magnificent cascade. The laws that dictate how a neutron behaves in a nucleus are the very same laws that, when scaled up through cosmic violence, create the conditions for a planet to form and for life to emerge upon it. We are not just living in a universe governed by physics, we are a manifestation of its most profound and interconnected principles. This final understanding weaves every thread of our story into a single, breathtaking tapestry. Our journey from the violent embrace of two dead stars to the planet we call home reveals a universe of profound connection and breathtaking beauty. The gold in a necklace, the iodine in our bodies, and the radioactive warmth deep within our planet are not separate things. They are different verses of the same cosmic poem, each one whispering a story of catastrophe and creation that unfolded over billions of years. To know that we are literally the children of colliding neutron stars fills us with a profound sense of wonder and a deep sense of place in the cosmos. It shatters the illusion of our separation from the universe at large. We are not just temporary visitors living on a lonely rock in space. We are the universe itself, become conscious, looking back at the stars from which it was forged. The iron in your blood once coursed through the heart of a dying star. The calcium in your bones was sintered in the blast of a supernova. And the very elements that allow your brain to process this incredible story were themselves processed in the most extreme conditions the universe can muster. This knowledge transforms our perspective on the night sky. It is no longer a distant, cold canvas of anonymous lights. It is a living chronicle of our own ancestry, a map of the violent and creative events that led to us. Every twinkling point of light holds the potential for new worlds and new life. each one a testament to the same physical laws that brought our own world into being. As we continue to explore the cosmos with ever more powerful tools, let this fundamental truth guide us with a sense of humility and boundless curiosity. We are exploring our own extended family, seeking out other possible manifestations of a universe that has learned to look upon it